Hello students, today we are going to begin our very first lecture on this integral and vector calculus, and as I have told you that we'll basically start with the integral calculus section at first, and then we will move to the vector calculus part. So to begin with, just to give you an overview of the course, I've already done that in the introductory video. So we will first start with partition and concepts of Riemann integral and properties of Riemann integrable functions and so on. So today we will start with the partition, and we will try to explain the concepts of Riemann integrable functions. So let's first of all, in integral calculus up until your +2 level, you may be familiar with integral of the type fx dx. So this is basically an indefinite integral, and you also have done something like integral from a to b fx dx. So this is basically a definite integral, and we know that if we integrate this function, so this function fx, they most of the time they are very nicely behaved functions. So you can do integration or you can do differentiation of these functions because they are very well behaved in a way. And one such example could be that let's say example 1. So you have integral of x square dx, and if you integrate, then it's basically x cubed by 3 plus c, where c is any arbitrary constant. So you can see that the answer of this integral on the left hand side is basically a very nicely behaved function. So x cube is a continuous as well as differentiable function, and c is basically a constant function. So it's always something goes in the direction of finding the derivative of this right hand side. So if you differentiate this right hand side, so if we differentiate the right hand side, x cubed by 3 plus c, then this will be basically x square, because the derivative of the constant is 0 and derivative of the first term is basically x square. So it's always goes in a way that how can we find the derivative, how can we find the derivative of this function x square here. So whatever function you have in the integral, so these functions, these fx here, they are called as integrand. So whatever integrand you have in the integral, they can be a differentiation of some other function, and these functions fx, they are sometimes called as antiderivative. So in a way you have to find out a function which is a derivative of this function fx, and that will be your answer to your integral. So this is what we did up until our +2 level, and now we will basically look into the Riemann integral. So those integrals were quite simple, where you had to find out the derivative of the function fx in the integral. In Riemann integral, we'll look at integrals in a little bit different way, and we will start first of all with partition. So just to start with partition of a set. So by partition of a set, what do we mean by that? So to start with, we will assume let a to b be a closed and bounded interval. So of course it is a closed interval and a and b are finite. Then a partition of AB is basically a finite ordered set P which is defined as, let us say, x0, x1, x2 up to xn of points of AB, which means that that is A is equals to x0, x0 less than x1, x1 less than x2, and so on. So, it is basically finite and it is also ordered. So, you have x0 less than x1 less than x2 and so on. So, such kind of finite ordered set P is basically called as the partition of AB, of this closed interval AB. For example, we can consider, for example, P equals to 0, 1, 2 up to 5 is a partition of A to B. This is first example. Second example could be P equals to 0, 1 by 2, 1 by 3. So, here A and B, here A is 0 and B is 5. Similarly, for example 2, if we consider P equals to 0, half, 1 by 2, 1 by 4, 1 by 5, and 1, then this is a partition of A to B, where A is 0 and B is 1. So, you can consider any type of partition for this interval A to B, and the family of all the partitions of AB is denoted by curly P, excuse me, let me erase this. So, it is denoted by curly P of AB. So, of AB. So, this is basically the family of all partitions of the closed interval A comma B. Now, if we let me go to a new page. Now, if we assume that P is one such partition of the closed interval A comma B, where our P is basically consists of x0, x1, x2 up to xn, and such that A is x0 less than x1 less than x2 up to xn, then this P divides the interval A comma B into non overlapping intervals, x0 to x1, x1 to x2 up to xn minus 1 to xn, where our x0 is A and xn is B. So, if we consider a partition P of this interval a comma b, which is basically our given closed interval, and if this partition P is defined by this set x0, x1, x2, x3 up to xn, then this P will divide this closed interval into non-overlapping subintervals. So, if you take the union of these subintervals, then in that case you will basically get your closed interval a comma b. Now this term here, this term here non-overlapping, it means that these subintervals x0 to x1, x1 to x2, I mean they do not intersect, I mean they don't have any points common except for the end point. So that means x0 to x1, so where this interval x0 to x1 ends, you have interval x1 to x2 beginning from there, but they don't have any other common point. So that means these intervals, they are non-overlapping. And in other words, it means that if you have your interval a to b, let's say, then in that case your x0 to x1 will be here, then x1 to x2 will be beginning from here, and so on. Then you have xn minus 1 to xn, which is basically your point B. So that's how these subintervals are defined. We can look into one example. So one such example could be the partition P. The partition P equals to 0, half, 1 by 3, 1 by 4, and so on up to 1, let us say, divides 0, 1 into non-overlapping subintervals given by so those subintervals are 0, half, sorry, 1 by 4, 1 by 3, half, and sorry, 0, 1 by 4, 1 by 3, or we can have this as 0, 1 by 4, 2 by 4, and then 3 by 4. This one will be much more interesting. So let us say you have 0, 1 by 4, 2 by 4, and 3 by 4, and then I am taking the end point as 1, just to make the concepts a little bit clear instead of complicating it. So 1. Then in that case the subintervals can be given by 0, 1 by 4, 1 by 4 to 2 by 4, then 2 by 4 to 3 by 4, and finally 3 by 4 to 1. So this partition P, which has points as 0, 1 by 4, 2 by 4, 3 by 4, and 1, will divide the interval 0, 1 into non-overlapping subintervals given by these 4 subintervals. So this is an example of a partition for the interval 0, 1. Now that we have cleared out the concept of partition, we will basically look into the Riemann integrability, because Riemann integrability involves these concepts of partition and subintervals. But before we do the Riemann integrability, we will look into what is upper sum and lower sum. Sometimes they are also called as well, Riemann upper sum or Riemann lower sum. So to do that, we will start with a new page actually. So again, so our point of discussion is upper sum and lower sum. So upper sum and lower sum. Again, we will assume that let a comma b be a closed interval. So just to give you an idea, when we say a closed interval, that means both the endpoints of that interval are included, and when we say an open interval, then the endpoints are not included, and then you write it open interval something like this. So this is the way to write an open interval. All right. Now, in this case, we will always start we will always take a closed interval unless we are told otherwise. Now, here we take AB as a closed interval, and F mapping from A comma B to R be a bounded function in R. When we say bounded function, it means that it is bounded from above, it is bounded from below. Otherwise, we will say that f is a bounded function from above. That means it may not be bounded from below, and vice versa basically. Now, for example, when we say that a bounded function f(x) equals to, let's say, x square between the interval 1 to 2 is a bounded function. So in that case, the upper bound would be 4 and the lower bound would be 1. So that's what we mean by the bounded function. And we say let P be a partition of f of not f, but it's the partition for the closed interval a b. I beg your pardon. So it's the partition of the closed interval a b, where our partition P has the points x0, x1, and so on up to xn. And again, it follows that a equals to x0 less than x1 less than x2 up to xn minus 1 less than xn equals to b. So since f is bounded on AB, then it must be bounded on xr minus 1 to xr, where r can be 1, 2, 3 up to n. Here the idea is, I mean, if you have a function f which is bounded on the whole interval ab, then certainly it is bounded on every subintervals. So here xr minus 1 comma xr can for every value of r can be of any one of those subintervals, and if the function f is bounded on the entire interval, then obviously it will be bounded on that one small subinterval. For example, let us say we have fx equals to x square, and our closed interval AB is equals to 0 comma 1. So, where a is 0 and b is 1, then the partition P we can consider as 0. We divide it in 4 intervals. So, 2 by 4, then 3 by 4, and 0, 1 by 4, then 2 by 4, then 3 by 4, and then 1. Then this P partition P divides this interval 0 comma 1 into non-overlapping subintervals, and you can see that if we pick any one of these subintervals, so here the possible subintervals are, 0 comma 1 by 4, then we have 1 by 4 to 2 by 4, then we have 2 by 4 to 3 by 4, and we finally have 3 by 4 to 1. So, these are the 4 subintervals for this closed interval AB, and if you consider any one of these subintervals, you can see right away that this function f is bounded. It is mainly because of the fact that the function f is bounded on the whole interval AB. So, it will be always bounded on one of these subintervals. So, a similar condition holds here as well, and from here we can also see that if the function f is bounded on the entire interval AB, then in that case you have an upper bound and a lower bound for this interval AB. However, if you consider these subintervals, then on each of these subintervals you have an upper bound and then you have a lower bound. So, you can see that on this interval 0 comma 4, the lower bound is 0 and the upper bound is 1 by 16. However, in the interval 1 by 4 comma 2 by 4, your lower bound is 1 by 16 and upper bound is 1 by 4. So, similarly, on every one of these subintervals you will get an upper bound and then you will get a lower bound. So, now we will define basically these upper bounds and lower bounds for the whole interval AB and also for these small subintervals. So, for this function f, now we are back to this definition. We write let m equals to supremum of all the x in AB such that supremum over all the x, supremum of the function f(x) for all x in the closed interval AB, and small m is equals to infimum of the function f(x) for all x in the closed interval AB. So, this supremum and infimum are the upper bound and the lower bound for this function f(x) on the interval a comma b. Similarly, now for these subintervals xr minus 1 to xr, we define capital MR as the supremum of the function f(x) on the interval xr minus 1 to xr, and small mr is equals to infimum of all the x, infimum of the function f(x) for all the x in xr minus 1 to xr, where r is running from 1, 2, 3 up to n. All right. Okay, this page is full, so we go to the next page. So, from So, in the previous page, so here basically what we see is as I was talking in this example, f(x) equals to x square. So, here in this case we see that on every subinterval we have a lower bound and we have an upper bound, but at the same time for this interval 0 comma 1, the whole interval, we have a lower bound as well as we have an upper bound. So, now there is a relation between the lower bound and upper bound on the whole interval and the lower bound and upper bound on each one of these subintervals, which means the lower bound on this interval, on this small subinterval on this small subinterval 0 comma 1 by 4, the lower bound is 0. However, the lower bound on this interval 1 by 4 to 2 by 4, it is 1 by 16. Similarly, lower bound on this interval is 1 by 4 and so on. So, that means the lower bound on this whole interval 0 comma 1 will be either less than or equal to the lower interval on all the lower bound on all these subintervals. Does that make sense? So, the lower bound for this whole interval 0 comma 1 is either equal to the lower bound on these subintervals, in this case for the first interval, because the lower bound for the whole interval is 0 and the lower bound for this smaller subinterval 0 comma 1 by 4 is also 0. So, it is equal to actually, but as we proceed along these subintervals, we can see that the lower bound for this whole interval 0 comma 1 is either equal or it is less than, because on all of these subintervals the lower bound is not 0, it is either 1 by 16 or 1 by 4 or something like that. So, that means there is a less or equal to relation between the lower bounds, and that relation can be written as in this fashion. So, we can write that relation as small m is less or equal to small m r. So, the lower bound of the function f on the whole interval will be less or equal to the lower bound of the function f on all of these subintervals, and of course, the lower bound on all of these subintervals will be less or equal to the upper bound on all of these subintervals. So, this from here to here it is obvious. Now, upper bound on all of these subintervals will certainly be less than upper bound on the whole interval, because when we talk about the upper bound, we are taking the maximum value possible for the function f(x) on that interval 0 comma 1, and since the interval 0 comma 1 was divided into 4 subintervals for that particular example, we are taking the maximum value of the function, and it can be attained on any one of those subintervals, and basically we are taking that particular value as the supremum or as the upper bound for that function f. However, in rest of the subintervals, of course, we have an upper bound. Of course, the function f has a maximum value at some point, but that upper bound is always less or equal to the upper bound of the function f on the whole interval 0 comma 1. So, that is why the upper bounds on all of these subintervals will be less or equal to the upper bound of the function f on the whole interval. So, that upper bound is denoted by capital M, and here we have r running from 1 to 3 up to n. So, this is a very vital relation, and this relation says that the lower bound of the function m of the function f on the closed interval a comma b will be less or equal to the lower bound of the function f on all the subintervals, which is less or equal to the upper bound of the function f on all the subintervals, which is less than or equal to the upper bound of the function f on the whole interval a comma b for r running from 1 to 3 up to n. And we will conclude this lecture until here, and in the next lecture we will begin with upper sum and lower sum, and then we will introduce the concepts of Riemann integrability.